Hi, everybody. I'd love to introduce Thomas Hermans from Ghent University, who's been doing a lot of work on subsurface hydrology and uncertain quantification of the stuff, and he'll share that with us today. Yeah, welcome, Thomas.
Thanks, Greg, for the introduction. Before I start, I wanted just to thank all the collaborators that contributed to this work. Some postdocs, some PhD students. There are too many to name them. And before I start this talk, where I'm going to describe how we are using in my group numerical models to try to quantify uncertainty quantification in the subsurface, I just wanted to tell a bit who I am. So I have a PhD in applied geophysics from Liège University in Belgium. I spent some time during my postdoc at Stanford in the group of Jeff Cars. I know he gave a talk a few years ago or 2 years ago or something also. So you might relate to what he's doing in my work. And then I joined Ghent University in 2017, first as an assistant professor, and I'm an associate professor. And I have broad research interests. So I come from geophysical inversion, but I applied also geophysical techniques for monitoring, then doing a lot of groundwater models, uncertainty quantification, as you mentioned, and also more recently, geothermal energy research. And yeah, here you see people currently in my group. So I'm supervising 4 postdocs and 8 PhD students for the moment. But what I wanted to talk to you today is how we can try to quantify uncertainty in the subsurface. And before doing so, and before doing what and before showing what I'm actually doing in my research, I wanted to say a word about how difficult this is. And I'm going to use an example, which is coming from the field of hydrogeology or subsurface hydrology, which is the calculation of wellhead protection area. And you might wonder what wellhead protection area is. It comes basically from the protection of our groundwater resources. So you might know that groundwater contributes to about 50% of the drinking water that is produced in the world. It's much more in some countries, a little bit less in some others, but it can go up to 100%, for example, in arid area. And the way we extract this groundwater is by drilling some wells. And then when we drill some wells, we extract water out of it, and this creates what we call the cone of depression, which attracts the water from far away from the well towards the well. And in the US and in Europe, there is a concept, which is this wellhead protection area, which is that the water before reaching the groundwater is actually infiltrating from the surface. And so we should protect the land around the well so that we are not going to contaminate it. And then by applying some computation, we can translate what we call the travel time, a time it will take for a droplet of water that would infiltrate here on land before it reaches the well. And defining this is important because around those wells, we might forbid some kind of activities that might be dangerous so that we can protect our groundwater. Where I live in Belgium, we have this kind of things along the road, even to tell you that you are entering such a protection zone with a phone number so that you can contact in case of problem. And I'm going to use this example first to illustrate what we are doing. But before we can even do that, we have to wonder what is the subsurface about. And this is the first problem of the hydrogeologist, as I call it. It's that our representation of the subsurface is really based on sparse and local data. So we might have a few boreholes. You have here an example of what a borehole could look like with an interpretation already of what we call the lithology, the different layers that we have in the ground. But actually, we know only at the location of the borehole what we have. And in between, we have to make some interpolation or some interpretation. And this is something which is not so straightforward because geology is far from easy in some contexts. And so the question is what happens between those boreholes. We can also collect some other data, what we call dynamic experiments like pumping tests that can also give us information about the properties, but it always remains quite limited. Sometimes, if you're lucky, you can do geophysical exploration. This is what I do in my work as well. When you collect data between boreholes indirectly using some sensing techniques, and then you get an idea of what is between, but in an indirect way, and often through blurred images. And so the first question is, how can we deal with that, and what can we do about it? And the classical way then, in such a context where we have sparse data, to calculate this wellhead protection area would be to use the data that we have, both those boreholes, but also those dynamic experiments that I talked about, and apply an inversion or calibration process so that we get a model. And this model would be a representation of the subsurface properties that can allow us to calculate this wellhead protection area. Typically, it would be, in this case, a distribution of the permeability of the groundwater layers. And this inversion or calibration is quite a complex process that requires to define how the geology is and often to make a lot of simplification. But assume we can get such a model, then based on this model, we'll be able to calculate this prediction wellhead protection area. This is what we call the prediction, and this would be then a surface area at the land surface. So in theory, we can do that. It requires some work. We have to spend a lot of time in this inversion process to make it work, but at the end, often the results are a bit disappointing. And this comes from the fact that to apply the inversion that we do, we need to make a parameterization of the subsurface, often through defining zones. We have to define some boundary conditions, but also just the limit of the model. And often this implies a lot of simplifications, which means that any hydrologist that would work on this would get another solution because he would do things differently. So the solution is non-unique. That's a basis for studying uncertainty later on. But also the models that we are often too simple. And once we are looking at a target, so this is this travel time that we want to calculate before a potential contamination zone in our well. Well, if the calculation that we are making with our model is the black line, and that suddenly we can do a field test that would give us actually the actual travel time, we often see that we get something completely different. So our models are actually reproducing the data that we are collecting, but they are not able to predict correctly what we actually want to predict, to forecast. So it means that, again, we should allow some uncertainty quantification so that hopefully we don't provide only one value which is wrong, but a range of value that encompass the actual observation.
So question.
Yeah.
To understand the scale of this problem, so you have boreholes that give you the kind of layers that exist at that location. Do you have information about pollutant arrival times, like if you put radioactive tracers, collect them later on, or other heterogeneous data sets?
Yeah. I'm going to illustrate this again later. So indeed, the data that we would use are geological data at some borehole location, and then indeed tracer experiments that are simulating how a contaminant would flow between point A and point B.
Okay. And do you have seismic experiments as well? Like you have thumb trucks?
So you can use geophysical data. Often in groundwater, we're not using seismic data because we are targeting more shallow reservoir, where the seismic data are not so good on land. But we are using mostly electromagnetic data. So it can be from airborne data or ground-based data that gives us information on the electrical resistivity, for example. Why the electrical resistivity? It's because the water is impacting a lot the electrical resistivity, of course, the water content, the water quality. And so it's a way to image, for example, those layers. I'm going to quickly give an example later on.
Excellent, thank you.
That. Okay, so now I introduced already that we have some uncertainty, and so we would like to take this into account. But that's the second problem of the hydrogeologist, of course, is that this inherent model uncertainty is propagating into the model prediction. And so if you want to make decision making based on a certain outcome, we should allow for multiple realization. And because there are many models that are possible, there are also many outcomes that are possible. And so we should find ways to to calculate this in an efficient way. And that's another problem, because I'm sure you're familiar with stochastic inversion and stochastic problems, where we are trying to calculate not only one solution, as I shown before, but we want to calculate the full posterior distribution. So it means all the possible models that can explain the data. And actually, this can be done. If you look in the literature, there are ways to do that through Bayesian inversion. And one way to do it is to use Markov chain Monte Carlo, which is a sampling technique that allows you to sample the posterior distribution. So there is nothing preventing us to apply this to groundwater-related issues. But still, there are a few problems with it. It's that it's extremely computationally expensive. It might require millions of iterations to converge towards a solution, which means that it's only feasible if the number of parameters is low. And actually, the subsurface is full of different, so the dimensionality of the problem is very high because we have many parameters. The solution depends on how we define the prior distribution. So it means all the hypotheses that we have on the geology can be translated into some model parameters, which means that often this kind of solution is not really accessible for complex problems like we are solving in the groundwater world, I would say. And so what we would like to propose, it's an alternative to that. And I call it Bayesian Simulation-based Learning. But the reasoning behind it comes from the fact that either in the deterministic inversion or in a stochastic inversion, we spend a lot of time in the inversion part. So it means finding model parameters that can explain the data set that we observe. But often we are more interested in the target, so in the wellhead protection area, for example, in this case. And so if we could find a learning approach that would allow us to go directly from the data to the target, instead of going first through a model, maybe we would win some time and we could do it in an efficient way. The problem is that when we apply machine learning, we need training data sets. And in the subsurface, we are missing the repetitions that would allow us to train a model just based on existing data sets. This is something that can be done in surface hydrology, for example, because we have plenty of data sets looking at the time series of discharge, for example. But for the subsurface, we don't have that. We don't have a lot of data, and we don't have enough repetition. And this is where the idea of using numerical models as input for learning was actually born. So the idea is that we can use numerical models that are mimicking what we expect from the subsurface. And for those, we can generate both the data set that we would like to acquire and the target, the prediction that we want to make. And we can generate as many of those training samples as we want using our numerical tools so that we have a large enough data set. And then once it is done, we can learn a direct relationship between the predictor and the target. We still want it to be Bayesian, so it means we wanted to do it under uncertainty because uncertainty is so important in the subsurface. So we need a learning process that can deal with uncertainty. And hopefully this will be helpful when we get some field data. So now I'm going to show you how we can solve the wellhead protection area with this idea of Bayesian simulation-based learning. And the idea is actually not so complicated, and it fits very well with what I just explained. So we simulate a subsurface model. So we generate many samples of the subsurface as we expect it to be. So you have here an example, which is basically an homogeneous model, simply. We start from an homogeneous model, which is then populated with some random variation around the mean. So this is done using Gaussian simulations, so something which is not too complicated, a little bit of geostatistics. And we generate many of them so that they are all different. So basically, we have some variations around the mean. And for each of these samples, we are simulating this wellhead protection area. This is our target. And then we are simulating those tracing experiments that I mentioned before. So a tracing experiment is injecting a dye tracer at point A, looking at how much time it takes to go at point B, and basically we monitor at point B the concentration time series. So we have a kind of curve like this with a peak and then a tail. And we can repeat this for many samples, so a few hundreds. And once we have that, we want to apply some statistical learning between them. This statistical learning doesn't have to be very complicated. In the early applications that we had, we were using mostly a dimension reduction technique, like principal component analysis. And the idea is that to do learning with uncertainty, it's really important to reduce the dimension so that it remains feasible with a limited number of parameters, being it with neural network or with more statistical techniques. It's really important to keep things simple. For example, here with PCA, we can reduce the dimension of this wellhead protection area to about 20 dimensions, so something which is quite limited. And for the data, similar. We can keep all the variables. Nevertheless, when you reduce the dimension, you always lose a little bit of information. And in this case, the wellhead protection area looks like a little bit like a potato, like you see the blue curve here, but the actual wellhead protection area is the red curve. So when we keep 98% of the variability, we can just simulate the potato and not all the variability. So the 2% represent this difference between the red curve and the blue curve. This is something we cannot achieve because it's too complex, too variable. So once we have reduced the dimension of both the data and so the predictor and the target, we do the actual learning. And in the early applications, we used a canonical correlation analysis, which is a statistical technique that's using eigenvalue decomposition and tries to maximize the linear correlation between two sets of variables. And you end up with a set of bivariate linearized relationships that can be characterized if the relationship is indeed linear by linear regressions, which means it can actually be solved analytically in this low-dimensional space. So something which is really interesting. If it's not the case, if it's not really linear, you can still use techniques like kernel density estimation to map the data into the target. But now we are in a low-dimensional space, so it means those variables, they don't have any physical meaning anymore, but they can be sampled. So this is the next step. You take your observed data, so you will have one set of tracing experiment. You project it into this low-dimensional space where we have done the learning. You get a posterior distribution in this low-dimensional space, and then you back transform it into the physical space. So those different steps can be done with a few computations, so it's really not heavy. And then you get what is nice, because you do it with uncertainty, you get the uncertainty quantification in your physical space of the prediction. And the example that is shown here, every white curve would be one of the samples that I predict with my after my learning, once I feed the observed data into the set.
So okay, when you say model here, so we should not be thinking about like neural net family of models. What I'm getting from you is that you have a bunch of simulation runs, and then what you're really trying to get is the covariance matrices between the parameters of the simulation, the input parameters, the unknowns, and the observed measurements, right?
Yeah. So basically, yeah. So the training sample that I'm having here. So every model is first a representation of the heterogeneity with a distribution of my model parameters in space. And then for each of those models, I can solve the groundwater flow equation, basically. And I need to solve those groundwater flow and transport equation to simulate my tracing experiments and to simulate my target. So basically, I'm running two sets of forward model runs, one for my predictor and one for my target. I multiply this by the number of samples. So let's say I have 1,000 samples. I need to run 200 forward models where I'm solving the groundwater flow and transport equations. And this is used for learning a relationship between the predictor and the target. You can use for that neural networks, but in this case, in this example, we're using things that are way more simple. Actually, we're just using eigenvalue decomposition and covariance matrix indeed.
Ah, wait. So now this may be, I missed it the first time. You're trying to connect the predictor to the targets. You're not going from models. So that red box, that's a covariance matrix. Could be any model, but in your case, covariance matrices. Predictor variables and the target variables, but not
exactly. So not with the model, not yet. So the model here is really just a way. This is the way we are using model is just to create a set of predictor variables and target variables before we even go on the field and collect the data. So the model is just a way for us to make sure that both the predictor and the target are physically realistic. You don't want to predict something that is not realistic because you will bias your learning towards something that is not possible. So our idea is really to use those models, those physical models, as a way to have realistic predictors and targets, things that we cannot have in reality because we cannot observe that many repetition, because we don't have any repetition. Any geological model is unique in the sense that you don't find the same geology at two different places. And so we use those numerical models to feed our learning algorithm, basically. I'm going to show later on how we can also access model parameters with this technique.
And as a general framework, predictor is observable and target is not observable. Is that right?
Yeah, so the predictor is something you can observe. So it will be the kind of data you can eventually collect on the field. While the target, you will never be able to observe, for example, the wellhead protection area. It's an output of the model, so you cannot observe it. You can possibly make sure that the one that you predict is wrong if you would collect a specific data set for that, but you cannot verify in reality this target.
Got it. Yeah. And then one more question about the bias of this process. So you've chosen the statistical relationship between predictor and target comes from the many model samples you have. And they come from some distribution you chose ahead of time, that was kind of uniform-ish because you sampled in a range. And it's not presumably the geology of a particular site because you didn't know it ahead of time. So how does the bias using this generic space versus my site affect the results?
Actually, you bring an important point. Actually, it is. You need to design your model here so that they are actually fitting what you expect from the particular site you want to work on. So it means that the learning that I'm doing here for the wellhead protection area of zone A, I cannot apply it readily to zone B. For zone B, I have to come up with a new conceptual model of the geology and populate this with a new range of parameters. So that's the tricky part of doing subsurface hydrology, is that you cannot translate a machine learning model to another site. It's not going to work. This is what we call the prior consistency. Yeah. So that's painful, but it's the way it is. We have to start from scratch again for another site.
Got it. That makes sense. Thank you.
Yeah. And so just to illustrate, so we tested the methodology first with like what we call synthetic benchmarks, where we actually know what the truth is, just to test if it's working. And you see here 4 different examples. So the black line is always the truth, and the red is giving you the uncertainty prediction for this wellhead protection area. And you see that we're not doing a bad job in predicting the range of uncertainty. So in this case, it's possible with synthetic benchmark to validate, of course, that it's correct. But in reality, it's not going to be possible. Just a word about the training size, because you might think that we need a lot of model to learn this relationship. Actually, it's not the case. We retested that and we found that after 400 samples, so we just need 400 of those subsurface model, we stabilize the prediction of the posterior distribution. So we only need 400 models to be able to predict this accurately. which means because we have 2 model runs for each model, one for the target and one for the predictor, it means we just need 800 forward model runs. Well, if you compare this to an MCMC approach, that would take probably several hundred thousands or even millions of run. The cut in the computational cost is really huge. So we are really winning a lot of time by taking such an approach. So about the limitation, you brought one already. It's the consistency, the fact that we made some prior assumption about the geology, which means that our conclusions are only valid if those assumptions are correct. So we have to try to check that when we actually collect real data. There is also no guarantee that it's going to work if we have a very complex relationship. And then we might have to investigate more complex way to link the target with the predictor, for example, through neural networks. But overall, it's a really efficient method because once the learning is done, you can also test any data set. And actually, this is really interesting because it opens for us the possibility to apply this to what we call experimental design. And experimental design is something I really want to talk about because it's about collecting the most informative data so that we can reduce the uncertainty. And the objective of an experimental design problem is basically, as I said, to find the data set that would allow you to reduce the uncertainty the most. The problem is that because the uncertainty is, the subsurface is uncertain and unknown, we cannot solve this problem in a straightforward way because any data that we would collect, we don't know what it is going to look like before we collect it. It means that we have to solve this problem under all possible range of data that could be sampled from our prior distribution. And in theory, if you would do that, the problem that we just solved, you would have to solve it for many different data sets. So if you would use MCMC, you would need those millions of runs, and you would need to do it a few hundreds times so that you get a statistically significant solution about which dataset would be the most informative. But you have just seen that I can now do a prediction very quickly, just because the learning step that I have made remains valid as long as my data are within this prior range, which means that I can now solve posterior distribution very quickly and in a very cheap way. And this is what I'm going to use to apply to the experimental design problem. Basically, I'm going to draw from my prior distribution samples to learn the relationship, as we have done before, the relationship between the predictor and the target. I'm also going to run some extra models that I'm going to use to generate just the data sets. And those are going to be example of data that I could collect on the field if I would go on the field. And for those extra models, I'm just going to run my learning algorithms and see what's going to be the posterior distribution. And I'm going then to compare a list of possible data sets, for example, dataset 1, dataset 2, dataset 3, and I'm going to look at which one is reducing the most uncertainty of my prediction. And then if I average over a few hundreds of those data sets, I'm going to get which data set on average is the most informative, considering my uncertainty. And know that I have this learning step that is done. This is very straightforward and very quick. It just takes me a few seconds to actually generate the posterior distribution. And here you see the result that we have obtained. So basically, you see here the same true model and how it is predicted from 6 different possible tracing experiments. So each is obtained from another location. And I'm obtaining this solution just by having 6 learning models, one for each well. And then what I'm doing is that I have to quantify which one is solving or reducing the uncertainty the most. And this is just done by calculating a data utility function. It's just calculating the difference between the blue part and the red part that I have here. And then I'm averaging over 250 different models, and I'm getting a range of data utility functions for all. And by averaging for each well, I can now tell which well is the most informative. And in this case, you see that I have different distribution for different wells, and wells 4 and 6 have the lowest uncertainty, so it means that they are the most informative. And I'm getting this with not a lot of computational effort compared to what I've done before for just one. It's just repeating 250 times the same bench of calculation and adding an averaging step on top of it. What is also nice is looking at combinations of wells. So now I can combine well 1, 3, and 4, for example, and see how they are reducing the uncertainty. And so what we did is to compare all the possible combinations of 2 and 3 wells out of those 6 wells. And we found that there is one combination that is the most informative on average. You see that some of them are actually quite similar. But if you look here, the step that you have is between using 3 wells and 2 wells. So it means that using a third well is always a good way to reduce the uncertainty in this case. And so this is something that was not possible before without doing some additional assumptions that we don't have to make. So basically, in the past, you needed to make some averaging based on not the posterior distribution, but an estimation of it, a quick estimation of it. So I think that it's really in this experimental design problem that the approach, this simulation-based approach, is showing the main advantage, because it's really quick now to solve very complicated problem. One remaining limitation is that we cannot do sequential optimization at this point, because when you do sequential optimization, you collect some data, you can reduce the uncertainty on your prediction, but you also learn something about your model parameters. So as long as you're not also trying to learn something on your model parameters, you cannot apply the approach to sequential optimization. And I'm going to show in the next slide how we can try to achieve this.
Question about
yeah.
I mean, when you do synergistic experiments, where you have multiple experiments trying to make combinations, this smells a lot like a correlation problem. I'm noticing you have a correlation-based model, and to find the best experiments, it seems like there's a space where you want uncorrelated experiments is the ones that make the best combination. I mean, is that right?
Yeah, exactly. Yeah. The thing is that because so if you would know what the true model would be, it would be very easy to define which combination would be the most informative. But because the subsurface is uncertain, you don't know what is under your feet. We have to repeat those experiments many times. And this is where having a fast learning algorithm would be efficient. So it's not just about it's not just about, so basically you cannot, it's about correlation, you're right, but because the model is so complex, it's not so easy to derive those correlation. And this is the way we are using it, is actually to use a few of those models to find the correlation or uncorrelation between data sets. But they are basically all somehow correlated, because they are all part of the same physical model, the same simulation. So they are all coming from the same physical model. So they must be somehow correlated to each other. The idea is really to just find a combination that it answers your question.
Yeah, it does. Thank you.
Yeah. Okay. So now I would like to add a layer of complexity, and I would like to solve for some model parameters as well. So I would like to learn something about the model from my predictor. So not only the prediction about the wellhead protection area, for example, but also something about the permeability of the subsurface. And to illustrate this, I'm going to take another example, which is coming from geophysical inversion. So I don't know if you're familiar with geophysics, but basically the idea is to sense from the surface something about the subsurface. So you want to find some geophysical parameters out of the subsurface, and that are going to tell you something about the geology. And often this problem is an imaging problem. So we want to find the spatial distribution of this geophysical parameter. which means that in the triangle that I've shown before, when we had the predictor and the target and the model, now basically the target is the same as the model. So we simplify it to just a two set of variables. We have a model of the geophysical parameters, and by solving the geophysical equation, we can get the corresponding data set. And on the field, we can collect those data, and by our statistical modeling, we hope now to get something about the model parameter themselves. So basically, we replace the inversion by a statistical learning in this case. The learning phase is the same, so you have to sample the prior model space. It's an example with 1D here, just to make it simple. We can go for each sample model towards the data space. We can learn this relationship between the two. And once we observe our field data, we can see where they lie in the dimensional space, low dimensional space here. We can get the posterior distribution and back transform it into the original space. So this is how we can do inversion. The technique that I'm going to use to illustrate is called nuclear magnetic resonance. It's not so important, but it's something you can also do in the hospital to image the human body, but we can also apply it to the subsurface. It's sensitive to protons, so to hydrogen atoms, which makes it actually sensitive to the water contents. So this is quite interesting for people dealing with groundwater. And basically, the kind of data we are looking is a decay curve with an initial value that tells us the water content, and a relaxation time that tells us how water is bound to the solid matrix. Just to give you an illustration of the dimensionality, when we collect those data on the field, we are sampling at very high rate. So we get very highly dimensional data set of almost 12,000 points. But actually, the correlation is so high in this data set that it can be reduced by principal component analysis to only 5 dimensions. And those 5 dimensions, they retain 90% of the variability. And we don't want more than that because the rest is basically noise. So the PCA step is also allowing us to filter the noise in this case. I'm going to illustrate this later on. For the data space, in this case, we're working with a 1D model with just a few layers, so we don't really need to reduce the dimensionality of that because it's a 1D example. If you would do it in 2D or 3D, we would have also to apply a dimension reduction to the parameter space. This is how it looks like after statistical learning in this CCA space. You see that CCA is a linearization technique, but you can get also nonlinear relationship, like you see here. You also see that some dimensions are not correlated anymore. So this is basically just uncertainty. You're not going to be able to resolve that. But you see that in this case, in the first 3 dimensions, you can say something if you know where your observed data are going to lie. Instead of using then linear regression with analytical solution, we use kernel density to sample the posterior distribution in this case. And then we can get posterior distribution in the low dimensional space for model parameters, and then we back transform them into the physical space, which is basically a model of the water content with steps and a model of the relaxation time with steps. You see in this case that the uncertainty is really good at reducing the uncertainty. It's because the data is actually not sensitive to the shallow part of the. So this is why we have here very large uncertainty. The dotted line shows you the prior model space actually. So we are only reducing at a given depth when we are starting to become sensitive actually to the water content. And for this example, we compare with MCMC approaches to be sure that we're doing things right. And basically, we get the same solution, but we overestimate the uncertainty. I'm going to explain this in a few minutes, but at least we are going towards the right direction, and we obtain it much faster than MCMC. So it gives us hope that we can actually get also model parameters with this technique. The reason why we overestimate the uncertainty comes from the fact that we are never running any forward model run during the sampling. So it means we can sample models that are actually not fitting the data. And this comes from the fact that you are doing this in a low dimensional space where we have no certainty that we actually fitting the data in the physical space. And this is actually what we see. We have some model here in red that actually do not fit the data. And if you look at where they lie in the statistical learning approach, they're actually out of the main trend. You see the main trend is here. We have a few models there, which means that when we are sampling here, we are sometimes going to sample some models in this area, and it appears that they are not fitting the data. So our idea is that we can probably improve the learning by doing it iteratively. And so we borrowed some ideas called iterative spatial resampling, and we apply it to our process. And we call it iterative prior resampling. And basically, the idea is that we make a first approximation of the posterior model, and we use it to refine the learning step by adding some models. And now the learning will focus more on the area where we have a high density of model. We have demonstrated that actually then we converge toward the same MCMC solution as the MCMC. I'm going to illustrate this later with a field example. Again, a few words about the training, because it's a little bit more complex in this case to work with the model parameters. We need a little bit more samples to train, and in this case, we observe that we need about 1,000 samples for the learning phase. So it's just 1,000 for our model runs, again, to compare with the millions of runs that would be needed by the MCMC. In this case, it even appears that it's faster than a deterministic inversion, because in a deterministic inversion, you have to calculate the Jacobian matrix, which is kind of expensive. And this is an example for our field data. This is how the field data looks like. You see that we have decay curve, but we have also a lot of noise. It's because the signal we are measuring is very slow. This is also why we don't want to keep all the dimension after PCA. We are very fine by just keeping the decay curve. And this is how it looks like after the first iteration. You see we still have a lot of uncertainty. But by iteratively improving the learning, I'm here zooming on the first layer, we can actually really reduce the uncertainty of this first layer as well. And now we have only models remaining that actually fit the data within their noise level. So it's something we are happy about. So it means that now we can also solve for model parameters with this simulation-based learning approach. We get results that are similar to MCMC, so it's always good to compare our method to the literature standard. And it's very fast and much faster than MCMC, so it's really interesting to apply this. And not because
So I think if I may summarize your approach, and I really want to nail down kind of how your insight differs from MCMC is. The impression I got is you want to do Bayesian inversion, and if you have a basic simulation, you can't do that. You mean simulations run forward, Bayesian inversions runs backwards. It's very complicated, which is why MCC is expensive. You have to sample forward runs of the simulation at carefully chosen points to do Bayesian inversion. And your trick is you have a certain a family of functions where Bayesian inversion is trivial, like if it's deterministic, it would be for perfectly invertible functions. For you, it's these correlations. And you're trying to find the closest function in that family that's easily Bayesian invertible by training that function in that family from forward simulation runs. So you have a statistical surrogate of the original simulation that's easily Bayesian invertible and roughly approximates the original simulation. Is that fair?
It's part of it, but what is really important to understand is that I'm not trying to approximate the forward model run. I'm really just trying to map the relationship between a predictor and a target. Now it happens that for the geophysical inversion, I'm trying to map, of course, the inverse relationship. So I'm still related to this forward model. So you can see it as a proxy to it, but I can apply it to anything, because basically what I'm trying to map is a relationship between two sets of variables that have in common that they are coming from the same subsurface model.
Good.
This is where the key is. So the key is that any set of variable that I can try to relate it here as in common that they are coming from the same subsurface model. And this is where these numerical simulations are so important and are actually a trick for me to leverage this learning approach. But for the rest, you're right. I'm trying to find a mapping of the inversion, and instead of doing the inversion in the physical space, I'm doing it in a low-dimensional space where I cannot use anymore the forward model. So I'm using statistical learning instead. And if the dimension is low, it can be very efficient to do it actually, because it's not difficult to map a joint PDF for 3, 4, 5 variables. If you have enough samples, this can be done. So that's basically the core idea indeed of this approach.
Okay, so this, I like that. There's two, very reusable components. One is the surrogate idea that if it's, let's say, a regular neural surrogate would be deterministic version. And the nice thing about that is it has a gradient. You can do fun things with gradients. That's one. And the other idea is that there's a bunch of state about the model you do not care about. And what you really expect is the things that you have experimental measurements for, satellite pictures, your electric measurements, or your tracer experiments. So some experimental outcomes and some aspect of unobserved state, but just the one you care about. And what you care about changes. It's WPA in one experiment, it's model parameters in another experiment. Just extract the one you want and connect those two via your surrogate. You want Bayesian stuff, so you do correlation-based surrogates.
Yeah, and that's really the key. And the key is that often the prediction you want to make is much simpler than the all complexity that you include in your model. Your model, in a numerical model, you might have like millions of cells, so millions of parameters. Well, actually, the prediction you want to make might be a simple curve that can be characterized by like 2 parameters if you take an exponential decay, for example. And so this is really the key. The problem is that we realize that sometimes you also need some information about the model parameters to do things right. And then you have to go back into some more complexity. And if I have time, the last example I wanted to show is this step in our sequential optimization. This sequential optimization is the idea that when you collect a data set, it allows you to reduce the uncertainty on your prediction, but it's also informative about some model parameters, which means that when you collect this data, instead of going to the next data set that will be the most informative by accounting for all the uncertainty you had before, you want to first stop a little bit, see if you can reduce the prior range for your model parameters so that you can be more accurate about the next data point that you are going to collect. It means that after each data, you need to solve the prediction problem, but also some kind of inversion. So you have to invert also for model parameters. And then you can solve this sequentially and look at, okay, now I've reduced my uncertainty on the model parameters. Then I can go to the next data point that will be the most informative. And just to illustrate this very quickly, I'm going to do it with a 1D example, which is based on the fact that if you look at the interaction between groundwater and surface water, there is an exchange often at the location of rivers. And you have an exchange flux between the riverbed and the aquifer and the groundwater layers. And if you fix the boundary conditions and you fix thermal parameters, you can actually compute this flux from a set of temperature measurements. So again, you can apply a deterministic inversion. But when you do that, you fix, of course, a lot of things. So you could also solve for it in a Bayesian way without fixing the temperature. As we have seen before, this is feasible, either with MCMC or you do it with this Bayesian simulation-based learning that I introduced. But now we also want to do this experimental design optimization. So we want also to look at which data point would be the most informative to collect to reduce the uncertainty. And so what we do is that we set all those parameters that we are not sure of. We set a prior range, and then we solve what we call the Bayesian optimal experimental design in a sequential way, where we're going to solve for each new data point that we collect, the estimation of this exchange flux, but also the estimation of those subsurface parameters. And then we're going to look at which would be the next data point to collect to reduce the most the uncertainty. And so the idea is just to solve at the same time for a target, but also for some model parameters. And here, because the relationship is much more complex, we have been using some neural network, in this case, a probabilistic Bayesian neural network, to make sure we can also predict the uncertainty. And so the target here is both a flux and a list of subsurface parameters. And we're predicting with uncertainty. And so we're predicting the whole PDF of them using Gaussian mixture model. And this is just an illustration of how PB and N are actually working. So it's with uncertain target, but also with a range of value for the parameters of the neural network itself. And here I'm illustrating how for one specific model this works. So basically, I'm collecting first data at the surface because this is cheap. This doesn't cost anything. So I'm measuring the temperature in the river. What's the temperature of the water in the river? And then I'm computing with Bayesian optimization which data point would be the most informative once I know the temperature of the water. And in this case, for example, it would be this point, which is situated at 1.1 meter depth. But on top of that, I'm also reducing the uncertainty on the flux. So this is here. So after 1 point, I also know in which range the flux is located. It's the yellow distribution there. But I can also reduce some parameters like the thermal conductivity. You see it's not much reduced after one iteration. And also the bottom temperature. But you see that one data point is not enough to resolve everything. And so I'm going to compute which is the next point to collect to reduce the most the uncertainty. And this is point 2, which is collected at 0.3 meter depth. And then this gives me the green distribution. And finally, I'm collecting a third point, which is at 0.9 depth in this case, which allows me to reduce even more the flux. But you see that the reduction is small. And it also allows me to resolve some other parameters. And I can continue like this until I don't have any reduction of uncertainty. But if I repeat this for different models and different value of the flux, you see that I'm getting different type of sequential optimization. In this case, actually, it's interesting to collect only deep model, actually to validate that the gradient is very small at depth. And I have a reduction, very high reduction of uncertainty of the bottom temperature, for example. And in this case, which is intermediate, you see that I have points that are more distributed between the top and the bottom. The difference with what I've shown before is that now I can do it on the fly. So you could imagine that if I have trained my model, I'm going on the field and I can collect a first point, and then my model is going to tell me which depth I should sample after that to reduce the most the uncertainty. And when we look on the average result, when we do that a lot of time, we observe that the optimum sequence can be very different depending on what's the true flux. So the sequential design here is really needed because if you would collect just on average, you would not have the most reduction of uncertainty. On average, we can still say that a shallow point is always needed to solve actually for the flux, and that a deep point is needed to solve for the boundary condition of the bottom temperature. We can also say that actually after 4 points, it's not really needed to collect a 5th point because we don't have any reduction of uncertainty afterwards. And you can see it there because basically this is the curve, and the pink things that you see here is the uncertainty that corresponds to uncertainty we have on temperature measurements. And after a while, you don't have any freedom anymore, basically, if you measure more points. So it's going to become actually unnecessary to collect more data. So this approach can also tell us when to stop collecting new data and when to stop spending money on collecting more data. So that's the end of my talk. I hope I convinced you that this approach of Bayesian simulation-based learning can be very efficient to solve future prediction of groundwater model, but also to solve geophysical inversion and experimental design. The learning can be done with basic techniques, statistical techniques, or more advanced neural network. It depends on the complexity. It has been benchmarked against MCMC, and we are way more efficient in terms of computational cost. There are some limitations, of course. This dependence on the prior model is a big one, but it's true for any stochastic methods. The consistency with field data is also something you have to check. So sometimes when you define your prior model, you make assumptions that are too strong, which means that you're not going to be realistic anymore when you go on the field. And when you have very complex targets and very complex relationship, it might be difficult to design a learning which is appropriate. But with the current research in machine learning, I'm sure that we can find a solution for that. For example, if you think about very complex models that are almost binary, they cannot be easily reduced by PCA, for example, but then you can use a conventional neural network, for example, to do it. It's an example where this complexity can reduce from 8,000 pixels to just 20 dimensions. The problem is that neural networks are also making things very nonlinear, so the learning approach is also becoming more complex. So you might need to combine a conventional network with a probabilistic neural network for your prediction with uncertainty. If you do images, often you can also drop a lot of complexity because you're not really interested in the full image, but you might be interested just in the interface. It's an example here where we're just interested in the interface between this blue and yellow zone, and this can be simplified by just something looking like this. So it's much simpler, and with 2 or 3 parameters, for example, you could do something like this, which is completely grid independent, for example. Or if you have things that are more complex and spatially distributed, you can also try to do it with global and local variables by using eigenvalue decomposition as well, and where you drop the local things that are less interesting, and you keep only the global elements that are actually often giving you the main trend. And sometimes you just have also to accept that you cannot predict everything, like we did for the wellhead protection area. And we just leave part of the variability out of the problem just to keep the things that are actually significant, like those global variables might be. Okay, that's it from my side. I hope you found it interesting. And if there are any remaining questions, I'm happy to take them.
So let me ask this one. A key point of your approach is that you don't do all unknown parameters. You just do the ones you care about. So you had this wellhead protection area. You have in many like service applications, you have like, where do I drill for this mineral? That's all you need to know what the deposit is, not everything. But that limits your scalability. So you cannot use that same model for other predictions. It'll stick to without one outcome you care about. So can you talk about the tension between having task-specific surrogates versus inferring all parameters at a high cost and then making many applications of that same model?
Yeah. So I think that the reason why we are focusing on part of our model or part of our prediction, it's because you can indeed reduce the dimension very easily. And reducing the dimension makes things easier, but also it requires much less training sample. So if you want to predict something which is complex, basically if you want to predict the whole model, then you will need many more training samples, and your neural network, if you're designing a neural network, will have to be much more complex. I think it will be possible in the future, and this is basically what I meant with this kind of dimension reduction. And so you can represent something as complex as a binary image of several thousand samples with just 20 dimensions with the appropriate neural network, which means that I think it would be possible to predict also all of it from geophysical data, for example. You would just need to work a little bit on what would be an appropriate mapping between them. And so the appropriate design of the neural network, for example. So I think it's possible, but it's also good to realize that you don't need everything. And there are things that actually cannot be resolved. And so I think it's probably sometimes we want more indeed. And sometimes you get the prediction and you say, okay, I would actually also need to get some model parameters. But there are also ways to combine both approach. And as long as it's not feasible to solve fully for the model parameters because it's completely too expensive, I think it's an elegant way to focus on the prediction and maybe some of the global parameters of your model instead of everything. You will still learn a lot from that.
Yeah.
And a lot of the uncertainty will remain anyway. Yeah.
Okay, so then just one more thing. It appears that a lot of your uncertainty about like the fact you have to train for every separate site is because you don't have a notion of the common geology. I guess what I have in mind is if you were able to couple your geophysical model, like the local one, to the tectonic model of how this terrain comes to be, that would be common across all terrains, that coupled model might have fewer parameters that you have to like choose ahead of time, like choose manually. So to what extent, I guess, can combining more models that constrain the space be viable here?
Yeah. Actually, it's something I haven't included in the presentation here, but it's something we have done already. So it means that so you don't have to define it necessarily as a groundwater model. Indeed, you can define it as first a geological model, and this geological model can be translated into more sub-models, when one would be the groundwater one could be a geophysical one could be a tectonic one. But if you go to that level, indeed, you just need to define things in a hierarchical way. So you have to define first the thing that matters and that's going to impact the others, and you do it in a sequential way. It can be done. It's not much more complex. You just add layers of parameters that are at different sublevels. Of course, it can make things complex. I take an example. For example, if you want to couple a groundwater model with the geophysics, then you need to relate your hydraulic parameters, like the permeability, for example, or your geological parameters, like the fact that you have sand layers, to the geophysical parameters. And this is done through petrophysics. So you need a relationship that relates your permeability to the electrical conductivity, for example. And this is done by another level, which is the petrophysics relationship that might be in itself uncertain. So you add layers, but this can be done. And we're actually doing this. Yeah.
Yeah, and I'm fascinated because then presumably your experimental basis for your analysis becomes extremely wide because data from across the world is relevant to the same problem.
Yeah. But that would be, of course, very complex because, I mean, I know your point is, okay, if you make it more general, then you can model indeed different type of settings. But in the same time, it means you have to increase your training sets, right? And then I guess that at some point you have like a threshold between making things general and making things still completely affordable. Because if I'm doing something at the scale of the Earth, let's say it's possible, then I will also need to generate many models. It's going to take a lot of time, and so maybe it's not worth it anymore.
Yeah,
but for example, for the yeah. For the geophysical inversion, we are going to want.
Yeah. Okay. Yeah, that's good. Yeah, the heart of my question
so
was.
For the,
oh, can you hear me?
Yeah.
Oh, yeah. Okay, I think we're in sync. Yeah.
I'm hearing you.
Yeah, the heart of my question was the more comprehensive the model, the more experiments you need to parameterize it, but the more data sets are relevant for parameterizing it. And there's a race between too many parameters and more experiments to nail the parameters.
Yeah. So you mean that you can then use more real data to constrain the model?
Right. Measurements from more regions are applied to the same system.
Yeah, but the core idea is that you don't need that if you use the numerical models. Of course, you need numerical models that are physically realistic. The idea is that you would then create kind of database which is broad enough so that it can be applied right away to any dataset that you would collect. So let's say I have created a database to predict the wellhead protection area at any location in the world. Then you would just collect a tracing experiment at one point, and it would give you directly the wellhead protection area.
Yeah.
But of course, it would require to add some additional data, because otherwise your uncertainty would be very large. So you would have to tell, I'm in that kind of aquifer, like a sandstone aquifer. I have no fractures, and it would make the input then. The input would have to be broader, and you would need to give also input about the geology. So I think it's an interesting idea to investigate in the future. At this point, we are always doing the conceptual model of the geology before we start the training, to make it actually locally based. But it's an interesting idea to go towards database that would be more, that could be applied on more cases. I guess you have also the question because of what they do in surface hydrology, where you can more easily compare catchment that have the same characteristics. But they have many more observations. So right. I guess this is a difference between the surface and the subsurface.
Right, that's an important one. All right, well, yeah, thank you very much. This is fascinating.
Well, thank you for the invitation. It was a pleasure to be there.